When we hear the name Raptor engine, what instantly comes to mind is a tale of cutting-edge innovation and unmatched engineering brilliance. Comparing the evolution of these engines is like moving from a reliable pickup truck to a full-blown freight train. If Raptor 1 and Raptor 2 were like rugged trucks, tough but basic, then Raptor 3 is a massive semi-truck built for heavy-duty performance. And looking ahead, Raptor 4 will be that unstoppable freight train capable of pulling unimaginable weight. With 35 Raptor 4 engines working in unison, the Starship booster will unleash more raw power than any rocket in the history of space exploration. So what exactly makes the Raptor 4 such a monster of engineering? What secrets are behind its immense strength, and what exactly is pushing SpaceX to evolve this engine to its extreme limits? Today on TechMap, we're taking a deep dive into everything that makes Raptor 4 a revolution in rocket propulsion, from its early roots to the mind-blowing upgrades it's undergoing now. This story isn't just about numbers, it's about how SpaceX is redefining what's possible and reaching the very edge of physics to fuel the future of interplanetary travel. Let's begin. The Raptor 1 was never meant to be perfect. It served as a foundational test bed, a starting point for SpaceX to get its hands dirty with a new type of propellant known as methalox. Unlike traditional rocket fuels like kerosene, which is somewhat like using diesel fuel, effective but messy, methane offers a cleaner burn. It can even be harvested from the Martian environment using atmospheric and surface resources. Imagine a camping stove that doesn't need a gas can, you just make fuel from the world around you. That's the promise of methane and why SpaceX chose to pivot toward it. But it wasn't just about the fuel. Raptor 1 was critical in experimenting with a complex system called the full-flow staged combustion cycle. In simple terms, this means the engine uses two separate pre-burners, one for the fuel and one for the oxidizer, to spin the turbines that power the engine. This design allows nearly all the propellant to be used for thrust, resulting in higher efficiency and thrust-to-weight ratios. That's a big deal in rocketry. Still, Raptor 1 had its challenges. SpaceX had to wrestle with combustion stability, extreme temperatures, and materials breaking down under pressure. But these struggles taught them exactly what not to do, and what to improve. Armed with the lessons from Raptor 1, SpaceX launched the Raptor 2. This wasn't just a tweak, it was a major upgrade. Raptor 2 came with a clear focus: better performance, higher reliability, and easier manufacturing. They reworked materials, integrated advanced alloys, and adopted cutting-edge production methods. The results were impressive: higher thrust, better fuel efficiency, and greater adaptability across various mission types. One of the biggest wins was reducing the engine's need for constant maintenance. Stronger metals and smarter designs meant the Raptor 2 could be fired repeatedly with fewer concerns about wear and tear. The team didn't stop there. Improvements to the turbo pump and injector system also helped make the engine run more smoothly and consistently, minimizing failure points. With these major advancements, SpaceX wasn't just building better engines, they were laying the foundation for future rockets to break records. And that's exactly what happened next. Building on this momentum, SpaceX created the Raptor 3, an engine that wasn't just a technical upgrade but a total redesign. It was built for heavy lifting, and everything about it, from design to performance, was meant to push limits even further. The Raptor 3 is stronger, simpler, and smarter. It boasts a combustion chamber pressure of 350 bar, an absolutely record-breaking figure. To put that into context, the legendary F-1 engine of the Saturn V rocket managed only 70 bar. Russia's RD-180 engine reaches around 267 bar, while NASA's RS-25 hits 206 bar. But Raptor 3 blows past them all. It generates an estimated 269 tons of thrust, over 593,000 pounds. And that's not even its maximum. In real-world conditions, Raptor 3 can reach 280 tons of thrust at sea level and 306 tons in a vacuum. These numbers aren't just big, they're historic. What makes Raptor 3 even more impressive is how clean and compact its design has become. The internal structure is much more unified, with many of the previous components either hidden, removed, or combined. One key innovation is the integration of internal cooling channels right into the engine walls. This eliminates the need for a separate heat shield, which in turn removes the need for over 10 tons of additional fire suppression systems that were previously installed behind that shield. It's the engineering equivalent of decluttering while upgrading: lighter, cleaner, and more powerful. Another smart move in Raptor 3's design is the shift from bolted joints to welded connections. Think of bolts like screws in furniture, easy to take apart and fix. Welds, on the other hand, are like industrial superglue, permanent, sturdy, and hard to undo. By welding parts together, SpaceX improved the strength and reduced the overall weight of the engine. This kind of design is perfect for performance, but it does come with trade-offs. Repairs become more difficult because you have to cut the welds to get inside. But if reliability is the goal, then this approach makes perfect sense. Now comes the real beast, Raptor 4. This next-generation engine is envisioned as the final evolution of the freight train metaphor. It's built to carry the heaviest loads over interplanetary distances. The target thrust? Over 330 tons. That's enormous. With 35 of these engines strapped to the Starship booster, the rocket will produce a mind-blowing 11,550 tons of launch thrust. Nothing else comes close, not even the Saturn V or NASA's new SLS. Raptor 4 is being designed with even more simplification in mind, possibly eliminating all unnecessary or failure-prone parts. It's a living example of the engineering principle: the best part is no part. While Raptor 3 amazed us with its record-setting combustion chamber pressure of 350 bar, Raptor 4 is expected to go beyond that. But the magic doesn't stop at raw power. In terms of thrust-to-weight ratio, Raptor 4 is also a standout. Based on a projected thrust of 330 tons and a weight of about 1,500 kilograms, the TWR lands around 220, a huge leap over many other engines in history. To compare, the Merlin 1D used in the Falcon 9 produces 180 tons of thrust with a TWR of around 150. Raptor 4 leaves that in the dust, all while remaining efficient and reusable. But with all these gains, there are also new challenges. Integrating cooling circuits directly into structural parts means each component now serves multiple roles: structural support, heat management, and fuel transport. This complexity makes both design and manufacturing significantly harder. And while welded joints improve performance, they create maintenance headaches. If a part needs replacement, the weld must be cut, which is labor-intensive and risky. These are the trade-offs SpaceX has accepted in pursuit of higher performance and lower failure rates. It's all part of the philosophy: make it better, not easier. Reaching higher thrust and more extreme combustion pressures requires engine hardware that can survive truly punishing conditions. Even Elon Musk has acknowledged the razor-thin margin these engines operate within. On X, formerly Twitter, he posted that Raptor operates close to the ragged edge of physics. That one sentence says it all. SpaceX is pushing these engines to the absolute limit of what materials and design can handle. And they're not stopping. The evolution doesn't end with Raptor 4. Plans are already in motion for future versions, Raptor 5 and even Raptor 6, each one destined to push the envelope further. SpaceX is chasing a bold goal. They want to cut the cost of Starship launches to under $10 million. To do that, they need to lower the cost of building Raptor engines. Elon Musk aims for a cost below $1,000 per ton of thrust. That's not easy. It means improving how the engines are built and managing every piece of the supply chain with precision. So when will we actually see Raptor 4 in a real test flight? That might take some time. SpaceX doesn't rush new engine versions. Each one must go through intense testing. These tests include static fires and real flight trials. Right now, SpaceX is still working on the Starship Upper Stage Block 2. But their last two tests ended in explosions. That version uses the Raptor 2 engine. So we likely won't see Raptor 4 until the new booster version 2 is ready. Maybe then testing for Raptor 3 and eventually 4 will begin. The story of the Raptor engine is really a story of constant innovation. SpaceX has kept pushing what rocket engines can do. Each version improves thrust, performance, and design. And each version solves problems that held back the last one. It's been a journey filled with engineering challenges. But SpaceX has kept moving forward to meet its bold space exploration goals. You might ask, what's their method? How do they move so fast and still improve? The answer is in their approach. SpaceX doesn't build one perfect engine and stop. They follow a fast loop: build, test, learn, repeat. They make a prototype, test it hard, study the results, and make a better one. Even failures are seen as data points, not setbacks. The very first Raptor engines were like test labs. They had many sensors. These collected data on temperature, pressure, and how each part behaved under stress. That data helped engineers fix weak points and create stronger versions. Thanks to this approach, SpaceX reached the point where they can build nearly one new engine every day. And each version isn't just a small fix. It's often a major redesign. For example, they removed flanges and igniters, parts that were complex and prone to failure. This made the engine simpler, stronger, and cheaper. Behind all this is a smart design system. Every change is tracked. Every improvement is logged. Nothing is left to chance. What's more, these engines aren't developed in isolation. Every engine is tied directly to Starship development. Test flights give feedback. Engine data informs spacecraft changes. It's a tight feedback loop that makes everything evolve together. And failure? It's not feared. It's welcomed as the fastest way to make progress. But why Raptor 4? What's the need for an even bigger engine? The reason is simple. SpaceX is building a new Starship, version 3. It's going to be massive, around 150 meters tall. That's about half the height of the Eiffel Tower. To lift that kind of weight, the rocket needs over 10,000 tons of thrust. That's 40% more than the current Starship. Only one engine is being designed to meet that challenge, Raptor 4. It's aiming to produce over 330 tons of thrust per engine. Compare that to Raptor 3, which already hits 280 tons at sea level and 306 in space. Raptor 4 is pushing even further. It's not just about more power. It's about reaching the very edge of what physics allows in rocket engine performance. It's like trying to tune a car to go faster while using less fuel. Hard to do. But that's what SpaceX is attempting. And as engines get stronger, they also have to get smarter. Over time, SpaceX moved away from messy designs full of plumbing. Their engines now look clean and efficient. With Raptor 3 they took a big step. They built cooling channels inside the engine walls. No more bulky heat shields on the outside. It's like hiding water pipes inside a wall instead of bolting them on. This saved weight and made the engine more compact. Raptor 4 will go even further. It will likely remove more weak points and combine parts. This will make it stronger and easier to build. There's one more thing that makes Raptor 4 special: the thrust-to-weight ratio. This is a key number in rocket science. It tells us how much thrust an engine makes compared to its weight. Raptor 2 had a ratio of about 107. The Falcon 9's Merlin 1D has a better ratio at 180. But Raptor 4 is targeting 220. That's a huge leap. Imagine building a truck engine that's lighter than the old one, but can pull twice the load. That's what Raptor 4 aims to do. The result? Faster liftoffs, more payload, better fuel efficiency. All key for long space missions. With this engine, SpaceX isn't just aiming for orbit. They're aiming for the Moon, Mars, and beyond. Raptor 4 is the engine that could make a moon base possible. It could power interplanetary missions. It's a big part of Elon Musk's vision of putting humans on Mars. Why is this engine so important for Mars? Because it uses methalox fuel, a mix of methane and oxygen. And on Mars, these fuels can be produced from local resources. That means rockets can refuel on Mars, not just Earth. It's a crucial piece of the puzzle for long-term space travel. Finally, Raptor 4 helps SpaceX stay ahead in the rocket industry. It has higher thrust, better efficiency, and record-breaking pressure performance. Most engines can't match it. Think of it like the shift from dial-up internet to fiber optics. It doesn't just improve speed, it opens new possibilities. So, are you excited for what Raptor 4 could mean for space travel? Let us know in the comments.